All right, and third time is the charm. Welcome back, everyone. I am thrilled to introduce, coming to us from sunny Arizona, Nancy Cooke, the professor of Human Systems Engineering, where she develops methods for assessing individual and team cognition with applications all over the place, from knowledge engineering to healthcare, homeland security, remotely piloted aircraft, and emergency response systems. Let us welcome.
Not really liking this weather because the sun gets to be too much after Okay, I want to just tell you a little bit about my philosophy of human AI teaming. It's been a fascinating morning already hearing about it. I direct the ASU Center for Human Artificial Intelligence and Robot Teaming, and our philosophy at the center is that we should, which is what I think too many people do in AI development, we should not develop artificial intelligence to replicate humans. Certain things we can do well, and certain things we don't do well, but instead we should develop artificial intelligence to complement humans and make us into superhumans, doing things that we couldn't do before. So that's our philosophy, and in that light, one of the examples here of what we do, a chart, putting this making this kind of real, is the use of artificial intelligence to do something that humans can't do, and that is manage very complex missions where there's a lot of things going on. And so I did this work for the Air Force, more specifically for Space Force, and it was really strange. I got a call one day from the program manager at the Air Force, and they're like, "We need you to do something really risky and bold, but for cheap." I'm on it. I do. So we have a lot of custom distributed human machine teaming for safe and effective space-based missions. I want to thank the people on the team who have done this in collaboration with Katie Coleman, who happens to be a doctor of PhD, but she's also a former astronaut. And so we got a lot of our information from her, but a lot of other people who are on this team to do this really risky, bold, cheap work. We already know that there's challenges talking about space operations that can include not only some of the commercial vehicles, but International Space Station, all of the centers on Earth, Mars and Mars rovers, and maybe a lunar colony eventually. This is a complex system with lots of humans, lots of machines that are operating at different levels of artificial intelligence or autonomy. It takes place in a distributed, massively distributed socio-temporal environment. And there's a lot of challenges with communication. One of the big challenges is the latency from Earth to Mars, depending on the positioning of the planets. It can take between 3 minutes to 22 minutes to communicate, to get a response. So you can imagine how frustrating that would be if you say hello and 20 minutes later you get hello. Tasks are complex, much procedural detail. There needs to be very close monitoring of operations and teams with increasingly heterogeneous. So our solution, and I'll just jump ahead, was to have AI stand in as a mission manager. So we are going to have take signals from this large system, signals that are communication signals, physiological signals, vehicle positioning signals, and send them through an algorithm that does machine that does layer dynamics, so you're going this method, dynamical systems modeling, and it's able to identify anomalies in the system, and eventually, I'm not sure there yet, use machine learning to classify the anomalies as a particular type of anomaly, and then have AI monitoring this whole system for anomalous states and interjecting, maybe sending something to NASA Mission Control when there's an anomaly, it recognizes it as a type, and maybe suggests an intervention. To me, this is something that the human can't do, but perhaps AI can. So our objective with this work was to do a proof of concept, basically. We're going to start out by talking about some human-machine teaming issues in space that we identified through interviews with people who have been involved in space operations. And then we did implement those scenarios in a distributed human-machine teaming testbed and identify sensors to provide signals for the layered dynamics approach. And then so we started doing this, collecting demonstration data. In my lab, I've done lots of research with teams of like 3 or 4 people, sometimes agents along with the people. But in this case, we have 8 entities. It's not really as large as you would expect, but it's larger than we typically run. And rather than bringing people in 8 at a time, which many of you know is horrific, we are going to, I'm going to show you demonstration data that we collected on ourselves. And this had some nice features in that we could script it so that we knew exactly where the anomalies were and how they were going to play out. And then we could see if our technique can pick up those anomalies. And then we will do some analysis of the data. This is a real integrated approach to doing this proof of concept, in which we did the structured interviews. We used those to develop a scenario, and then we collected data on ourselves in that scenario and iterated. Okay, now the fun part was our structured interviews with people like astronauts and people who did space robotics. We talked to people who were at JPL who operated the rover. And we asked them questions that were related to 3 issues to try to get at the challenges in space: teamwork, human-machine teaming, and communication and coordination. We did 9 different interviews. And then we did a thematic analysis, iterative thematic analysis on those interviews. And basically this involves doing coding to generate identify themes, and then consolidating in the code book, transcribing the coding and doing iterative reliability. And we found these particular themes, along with human-machine teaming challenges. There were communication challenges, training challenges, distributed teaming challenges, and complexity challenges. And I'll go over those, but if you want to see the numbers of things, it turns out that communication and training were the most common kinds of challenges that were mentioned. And this is the human-machine teaming challenges and perceptions. That it's more like they talked about the rover and some automation like the robotic arm as it's not really like a teammate, it's like a kid and they're constantly worried about it. And one person said the AI probably doesn't care about the person, but that I think that is one of the things that's happening. And there's more and more AI that they have to contend with, so that is a big concern because they're in an environment that could be risky. One person who operated the rover says that when we asked about the rover as a teammate, they envisioned the rover as having about 75 people inside controlling it. So it's not really it does some autonomous things. They also had an interesting description of autonomy. What is autonomy? And there is really no autonomous system. You have a system that has autonomous functions. Some of them have autonomous functions, but you can't really call the system autonomous. There's usually mixed levels of automation autonomy. And when we talked about trust, there was a strong tendency for astronauts in particular to want to know everything about the automation, everything about the machine, everything about the robotic arm. And it's something, this trust in the automation is something that happens over time, like a friendship with a person happens over time. And they wanted to have complete control over the autonomy. They wanted to stop it, since it's getting too close. It's kind of like think about autonomous car. Do you trust it to brake in time? I have automatic braking, but I'm not going to test it because I'm not sure it's going to work. So with all of these challenges that we identified, we developed this scenario called Quest for Interphoto. And this was not so much developed by me, but by some really talented graduate students who were very creative. And the idea is that it's about 2030 and the Earth has run out of sources for energy, which is not that unbelievable, and that there happens to be some material that we're calling interphoto that's only found on the surface of Mars and the Moon that will provide a source of energy for Earth. But in this mission, this has to happen quickly because we're running out of energy. The goal is to collect this material and bring it back to Earth. In the meantime, we have a lot of predator anomaly detection, so we put a lot of perturbations into this scenario. During this scenario, which is a 15-minute scenario, there's things that happen. So we have a spacewalker who is at the International Space Station, and she's in this actual scenario, she's looking at the spacewalk, a VR kind of game. She becomes untethered, and one of this VR part happened is also taking heart rate variability from her in order to get a sense of stress workload. We have another perturbation that happens. There's a lunar colony. The lunar colony has a robot that's not so trustworthy and has a human. There's an asteroid strike that happens, which takes down their supply of oxygen, and they have to rebuild something quickly. That person on the moon is also being measured. We have a lunar orbiter and a Mars orbiter that communicate between Mars and the International Space Station. We also have a Mars rover. For all of these vehicles, we're going to be taking positioning information. We are simulating the orbiters using our UAV testbed, which provides positioning information. And all of this is tightly scripted, so they're supposed to be talking to people on, there's certain people that they're talking to. It's not, it's directed communication, so we have radios where they have push-to-talk buttons. If we push NASA Mission Control, they push to talk to somebody at the International Space Station. Not everybody hears this. And so I'm going to show a video where, I'm not going to show the whole thing, but there's a lot going on. People are talking at the same time. That's not what each individual is hearing, but that's what it's like. And just imagine being a human trying to monitor this system with all these signals, and you'll just be seeing the position, the communication signals, but there's also positioning and physiological signals that are coming in. So let me see this. Just play a few minutes for this. This is 15 minutes. See?
Everybody ready? 5, 4, 3,
Just sync it.
2, 1.
Delta to Charlie, take a look at your gloves. Make sure there's no tears. Houston has visual contact on helmet, and your heart rate and oxygen levels are in your chest if you need to.
Mars orbiter to mission control. Orbiter's current distance
Delta
from
to Charlie,
KGM
grab hold of the clip,
is,
fix it to the yellow handrail.
30. Continue to track Mars rover location.
Mars orbiter, this is NASA MCC. Copy all. Over.
Delta to Charlie, your toolbox is attached to your waist belt. We're ready for you to move outside. Grab hold of the yellow handle, pull yourself up.
A-okay.
Pull yourself up. Give us a wave, EV2.
This is JPL to NASA MCC requesting waypoint. Over.
Mars orbiter to mission control. Orbiter's current distance from KGM remain to be 30. Continue to track Mars rover's location. Over.
Orbiter, copy that.
Roger, stand by for waypoint. Over.
Delta to lunar orbiter, copy that.
Mars orbiter to mission
Delta
control.
to Charlie.
Mars rover is
Remember,
currently
pull the trigger
located at
on the hand controls to pull
BLO.
yourself
Over.
forward. Reach up to the handle on your right. Over.
JPL, this is MCC, currently located at BLO. Proceed to the next waypoint. Over.
Mars orbiter to mission control.
Or on your
Orbiter's
own
current
right.
distance from
MCC,
KGN
roger that.
is
On your next waypoint,
29.5.
over.
Continue to track Mars rover's location. Over.
Copy 29.5. Over.
So we have a husky
Alpha,
robot.
this is Bravo. Move to ROC.
There's more of it, but try to get the idea. Goodness. Okay, so that was our scenario, and it involves basically these 7 entities plus the Mars rover. So there's actually 8 entities plus the Mars rover. NASA Mission Control has a human, JPL has a human, International Space Station has 2 humans, the Lunar Colony has a human and a machine, and trusty robot. Lunar Orbiter is 1 human and a vehicle, same with the Mars Orbiter, and then the Mars rover is a machine. And we have a communication network that is fairly complex. Not everybody talks to everybody at the same time. Some people only talk to certain people. We also have in our radio system built-in delays. We didn't want to build in a 20-minute delay because our scenario is only 15 minutes, but we do have built-in 2-minute delays when we're going from Mars to Earth, which also be considered a perturbation. Okay, for our sensors, we have communication sensors. So we have a custom-made radio system. It looks like you're operating on a cell phone, but it's push to talk, depending on who you want to talk to. And we can collect data on who's talking when. And that's the communication data. We also use VO EEG sensors to collect heart rate data through an iMotion platform from 2 of the humans, from the one that becomes untethered and from the one that is rebuilding their oxygen. We have a Husky rover, Husky robot, which is the rover, and we take positioning data from it, as well as the command data sent from JPL. And there's delay between the command sent at JPL and the time Husky moves. We have these orbiter positioning and orbiter commands that are done through our command data. Okay. I want to give a shout out to Jamie Borman, who was at Georgia Tech, he's now at Arizona State University, and he has come up with this layered dynamics approach. He does dynamical systems analysis, and I'll tell you a little bit about this approach. He takes signals, all of these signals, and looks at reorganization, looks at entropy. And this is a windowed entropy. Every so many seconds, we'll take a reading on the signal. And when the system starts to reorganize, you'll see a jump in this next entropy. Now, there's lots of different system components. What the layered dynamics lets you do is look at all of these signals coming in at once. And when you see a jump in entropy, you can see other parts of the system that then cascades to. And so you get kind of a profile of what's happening, and in anomalies you'll see a different profile than you used to see. So here is an example of that. We have all these communication signals, the physiological signals, and the positioning sequence. And when there is a perturbation, like Charlie becomes untethered, you can see jumps in some of these, but not all of them necessarily. And this is what we want the AI to pay attention to and over time learn the meaning of these jumps. This is just looking at the communication layer. So different people are talking at different times, and it can become pretty complex. Lunar orbiters talking to Delta. And so we look at these over time and merge them into a communication signal. And then the same, the vehicle layer, which captures the orbiter position, trajectory, and speed data. And the same with the physiological layer. So what we're finding in this initial data that we've been collecting is that we are able to see changes in these patterns when there's an anomaly. And the next steps would be here. Leveraging our test bed, doing more scenarios and more variations to see what we can pick up and to start applying the dynamical systems measures to these data to continue that, continue the layered dynamics approach. And now we're going to also get a machine learning person who's going to be able to help us take those patterns, learn about them, and associate them with first an anomaly, what part of the system did it happen in, and then how can we classify that anomaly. And so what we're calling this system is Artificial Intelligence Management System, or AIMS, with the idea that this is something that AI can probably do that humans can't do. We're also considering this in the Air Force and the Navy for joint all-domain command and control, where you have lots of different entities all interacting in a distributed fashion. How do you possibly manage all of that? So this is one use of AI that I think could be effective. That is it. Yes.
Yeah, something. So, why would you use machine learning? Because this seems like very rule-based, right?
Yes.
So why use an unsupervised or a supervised, but like an unstructured learning mechanism?
It could be rule-based. Part of the problem with using machine learning with these data is that if you think about it, these anomalies don't happen all the time, so you don't have very many examples. So in this case, they're going to try to do machine learning and sparse data, which I think is going to combine some rule-based stuff as well. We haven't gotten to that point yet. But yeah, machine learning, as it's typically done, would be a big challenge because of the sparse data.
And you would assume that there are signals that you don't know about, right? So
yes,
things you want to
React to, but you don't have a rule for it because you don't know, right? And so maybe there's stuff in there.
So what it means is that the machine learning algorithm would have to understand what normal looks like.
Yeah, exactly. What is your target vector, right? At the end of the day.
And then
Exactly. Like, how would you define that?
Yeah, identify deviations from that.
But but I guess you could define things like, I don't know, minimal delays or minimal disruptions in some fashion, right? That's interesting.
So a lot of things could go wrong in the real world, right?
Yeah, and you don't know all of them, right? And so it's interesting, really cool application.
Yeah, I mean, it's an interesting problem. I mean, so some of the things you built into your scenario, like think of any science fiction movie you've looked at, right? It's always the unexpected thing that happens. No matter how well you train, damn, we didn't see that one coming.
So at a minimum, for those kinds of things, the AI should at least be able to detect that something's going on that I don't know what it is, but there's something going on.
Fix it.
Yes.
Have you already thought about potential machine learning models for those anomalies or predictions?
I have a person, a graduate student, who's working on that.
So somebody was asking, we've been trying like inverse reinforcement learning, demonstrations and things like that. That's
I can put you in touch with this person. Yes.
So I talked to people in the Air Force who are in air battle management. And very often these are people with decades of experience and a way of somehow assessing the battlefield. And I don't think they can tell you exactly how they do it, the same way that I cannot tell you how I balance myself on a bike. Mm-hmm. And I just have a very hard time thinking that we can say, you know what, let's just outsource it to AI to manage the complexity, the contingencies, the tactical and strategic assessment that just happens in somebody who has been doing it for 30 years.
I completely agree, and I'm all about human AI teaming.
Yeah.
And so I think this could be a source of information for whoever has to make those decisions, but the AI wouldn't be making the decision to like pull the plug on the spacewalker or anything, just giving advice to the human who's also has this kind of intuitive sense for what's going on. Yes.
Just to follow up on that point, because I think it's a good one. I mean, experts are really good at anomaly detectors, right? But like I said, they kind of recognize the anomaly in the moment and don't necessarily even know how to express it because it becomes so complex.
Have you thought of using the human as a sensor that then triggers the AI to then evaluate the context, right? I mean, that would be one way where it's not so much that the AI has to look at this or detect this blip, but the blip comes from the human, and then the AI basically takes the context.
Yeah, that would be an interesting approach, but I don't know how would a human, though, recognize anomalies in a system that's this distributed?
Right, so that I think becomes the interesting research question, which is now it's a distributed sensing system with humans as the distributed sensors, right?
Yeah, and that's why I was thinking of the inverse, because it's also based on demonstration of experts, someone who's kind of identifying it without having the ability to explain, that you could then kind of train a model to learn from those kind of expert decisions.
Right. So,
but the question is, are those sense-making activities, how do they take place?
Yeah. So again, I believe in giving humans superhuman capabilities, like Centaur chess, where you can team a decent chess program with a pretty decent human chess player and have something that'll beat the best grandmasters. And that's just because human intelligence is very different than artificial intelligence. They do things differently. They have different strengths and weaknesses. I liken it to teaming with a dog. It's not, there's pretty good human dog teams that do search and rescue, or human marine mammal teams that search for ordnance in the water. They don't have human intelligence, but they have the ability to do something that the human can't do. Right? So the dog has superior olfactory senses. The marine mammal has different capabilities, and so when you merge those, you get something that's beyond what we need.
I wonder whether we can apply down to earth, so to speak, to driving. Hundreds of billions of dollars have put into autonomous driving, yet to be delivered, partly because the way humans are able to assess the situation and make reaction is something that we have not been able yet to transfer to machines. And if we just take the other approach, which is let's find a way to help the human become a better and a safer driver.
Yeah, I think some tools like autonomous braking is different than having the whole thing drive itself, right?
Yeah.
And so there again, I think people are trying to replicate humans. Let's replicate the human driver, and I think that it's turned out to be sometimes not that good.
In our business, it's called AI versus IA. Where IA stands for intelligence augmentation.
Yeah, I agree. I know I had a run-in with, I hope there's no Elon Musk fans. I had a run-in with Elon Musk fans on the Twitterverse because they had me evaluate his humanoid robot during AI Day, and it was a pretty poor example of humanoid robot. It practically had to be pushed out by people, and it just went like this, and it took a step, and people were asking, isn't this a great accomplishment? I'm like, well, no, because we have robots that can do backflips and things. And why do you want this humanoid robot? He was saying that eventually this robot will be able to do everything that it can clean your house. It can go get groceries for you at the store.
You can drive a Tesla. An autonomous Tesla.
Yeah. There's speculation that he wants to put these humanoid robots on Mars and start a colony. So.
iRobot. I was just kind of curious. I mean, one of the challenges for any kind of system monitor for this are the communication delays, right? Because of Mars, it's 20 minutes each way, basically. So, oops, we've got a problem. It's 40 minutes before someone can say, hold on, we'll get on that. So, I'm kind of wondering about the time scale for the system monitoring. And once you detect an anomaly, you can't just call mission command because that's not necessarily where the problem is. Maybe something has to be done directly. I mean, it's probably. I mean, I'm sure you'll get there, but kind of what is the AI going to be able to do once it detects? Yep, there's a problem.
Yeah, I think we need some communication technology that speeds that up.
Yeah, warp drive.
I don't think AI is
wormhole.
Yeah.
I'm thinking about the astronauts on Mars saying, Houston, we have a problem.
Yeah.
And waiting for 40 minutes, right?
No, I mean, and NASA recognized. I mean, the crews are going to have to be more autonomous. So most of that's going to have to be, even if there's AI, it's going to have to be on board. Maybe you can have some, whatever you want to call it, some monitor or control system that is operating at a much slower time scale than now, where you have these. I'm on the moon, I got a problem here, I'm going to deal with this locally, or by the time mission control says, put a Band-Aid on it, we're dead.
Yeah, so maybe you could have AIs that do parts of the system.
Yeah, well, you almost have to distribute that whole monitoring because, the big brain, wherever you're going to keep that, it has a big picture, but its time scale is very slow compared to all of the kind of events that you built into your scenario that, half your team is dead by the time it's able to react.
Yeah. So there's lots of challenges. So I picked a risky, bold thing to do.
I'm glad you're getting the big bucks for it.
And on the cheap. Yeah.
Cheap, yeah. Okay. Thank you.
Thanks.
Thanks.